everyone, and welcome to this session on modeling and simulation with ropes and pulleys component library. This session focuses on the ropes and pulleys component library. It's not a real intro to MapleSim. People who have interacted with MapleSim and a causal modeling environment will be able to grasp the notes presented quicker, but I'm hoping that if this is the first time you see MapleSim, you still get value from the way modeling is done in our environment and how simulation can be used to answer engineering questions. So the library itself, it's 6 components, the rope group and the pulley group. The rope group is rope and chain and cable, and we'll start with rope and get to the other 2 as well. The pulley is the main component that we connect to redirect forces, but we also have winch to exert force on the rope, chain, or cable for wind and unwind. And the 3D version of that provides lateral motion of the rope and the winding increase in inertia or unwinding decrease in inertia. The library itself expands to many different subgroups and options depending on what component options you select. Some of these options we will touch in this session, some we don't. I hope that you still have time to explore the library on your own after this session. The components are compatible with each other, so you can use chain, rope, and cable with pulley, winch, and winch 3D. Without really spending too much time on this overview, let's just get to the first group of components, the most important. From the ropes, the rope component. The rope component is a 2-force element. It's always a straight and can be made not to exert any force in compression, only in tension. The one thing to note, and this would be kind of embedded in all the examples that I have included in the package that Rochelle mentioned, is that when we're using ropes, chain, and cable, we have to make sure that either end is defined properly, and that could be either fixing it to another part or giving it an initial condition. So the first examples that I have talk about the basics, the length, and how that would work. Let's take a look at the package. I should have it here. So we have about 20 examples here, and I don't think I'm going to go through all of them, but definitely suggest that you try them out. So we'll start with the very basic one. So let me jump into MapleSim. This one is very easy. So instead of opening the model, let's just build it together. We're just going to create a pendulum with a rope component. So we first need a fixed point in space, which is done by the fixed frame. And from the ropes and pulleys library that is sitting here, I will open the rope subpalette and dragging the rope component. Let me zoom in. Okay, so we'll connect here, click here, and then click here to connect the A side of the rope. So this side is going to be sitting at 0, 0, 0 in global inertia coordinate frame. The other one, the free end, we connected to a rigid body like this. And this rigid body needs to be given a position in space, as we just talked about. So I will use the initial condition for the position from the parameters associated with the rigid body, and set that to 1 meter in positive X, and also make that in force so that MapleSim will pick that as the initial condition for this point of our model. Before running the simulation, a general note that most, if not all, of the models with ropes and pulley tend to become stiff due to the stiffness in various members. You might have a small rope sections. We'll talk about those and see examples of that. So although non-stiff solvers would work, but a stiff solver would be recommended. So now that we have the model complete and the solver selected, we leave everything else untouched and run the simulation. So in MapleSim, for those who haven't seen this type of simulation environment, the process involved with generating equations from the component on the screen, and then simplifying those equations symbolically and converting them to a set of equations that are ready for code generation, then compilation, and then integration. So since this model moves in plane, I will switch to a planar point of view. And when I run this, it will act almost exactly like a pendulum. It has flexibility. If I go back to MapleSim and examine the rope, you will see that it has actual rigidity. For a 1 kilogram mass that is sitting at the end, it's very rigid, but it still technically is not rigid. So let's do a few more things with this before we move on. First thing first, let's look at the results. So we get the animation from the results of the simulation, but we can do more. We can look at the results of the simulation. So when this item is checked, anything that is probed, and we will see examples of that, will be automatically listed and plotted, which is the easiest way. But if that's not selected, or when you unselect that, you can start searching for variables in your system. So the ropes and pulleys comes with summary variables. One of them is tension. Here I can plot the tension in the this rope segment as the pendulum action is running, and you can see, as expected, at the lowest part we have the highest acceleration and we get the highest tension. We can also visualize this. This is one way that I'm going to visualize that with force arrows. So let's run that one more time, but just for the sake of presentation, I'm going to add a little bit of visualization to the end mass so that we get a sense of we have a hanging mass at the end. So I'm running the simulation again after these changes. One was I went to visualization section of the rope and activated force arrows and selected a scale of 25. So 25 newtons of tension corresponds to an arrow of 1 meter in the display, and added a purely visualization spherical geometry to the endpoint. So now we have a bit better situation in terms of presentation of the system going on, and we can see, as expected, the arrows show the tension in the system and as the variation of it. So this is the very first or hello world model to get us started. So I am going to go during this session between the slides that I have and the MapleSim for loading and running the models. So let's go back quickly and see what are in this group. So let's look at this one, or model number 2. Model number 2, instead of 1, we have a point in a space that we fix with given initial condition, but we have 2 ropes at 2 different locations that connect to it. One thing that you might have noticed is that when I was specifying this rope, I specified its endpoints, but I did not give it any length. So there's no parameter here visible right now that corresponds to the length of this rope segment. What happens is MapleSim will calculate that the length of the rope based on the initial position of its ends. So here we have one end at 0, 0, 0, as you can see here. The other one is at 6 on x-axis, and the mass is sitting at 1 and -1. So no other force being applied, and the expectation, and we will see that shortly, is that MapleSim will select the initial length for these ropes from the initial configuration of the system. And as a result, everything will just stay there. As I'm playing back the simulation, nothing will move because these are very rigid, stiff rope segments, and the mass is small, so it will just sit there. If I want to provide the length, there's an option for that. And if you go to number 3 model, it's somewhat similar. But if we take a closer look at the pieces, so the points are the same, 0, 0, 0, 6, 0, 0, and this one is at 1. So it is on the straight line. But if we look at this component, we will see that the option for use unstretched length has been used, and the length is given a square root of 2. For this one, the option for unstretched length is also used with the length of the square root of 26. Moreover, the option for no force in compression is used. And the reason for that, because we want to create a triangle, as we saw in this other example, when we put the mass here, the initial length will be smaller than the actual length. So we don't want the ropes to start in compression. So what we will do is that we set this one to no force in compression. Let's go ahead and run this. So the expectation for this would be the mass will start exactly on the line connecting these two fixed points. But since the lengths are bigger, it will drop down until the two rope segments are taut, and it will assume the final configuration. Very similar to the previous example, except in the previous example, we started here and let MapleSim do the calculation for us. Here we had to do the length calculation manually ourselves to get the same configuration. Just a point that comes very handy in terms of setting up your models. Going back to the next step, we have a lot of ground to cover. So that was two separate ropes connected to one object. We can have multi-segment rope. So it is basically the same rope, but it is broken into various segments. So let's look at example number 4. Go and open example number 4 here. There we go. So in example number 4, kind of has a little bit more happening, but the most important part of this example is that we have used the option for fixed end and unselected one. So when you drag a rope, chain, or cable to the screen, you will see that both fixed end A and fixed end B are checked. In this case, this one, it says end B is not fixed, which results in appearance of this 1D translational port. For rope, the second rope, side A is not fixed, which results in appearance of this translational port, and we connect them together, which means that this connection point can move left and right along the two ropes, and material is exchanged from one to another, giving us the capability to simulate or model sliding masses on ropes. You can do the same thing with cables and chains. Here, the simplest case is the rope. So again, similar configuration as we have seen before, but you can already see and imagine what will happen when we run this simulation, because this mass can slide with no friction along these two ropes. So it will start to slide to the right. And that's what happens. Also in this system, we, just like the first one that I created, I have activated the force arrows. We would want to see this nice summation of tensions that results the total force exerted. So that's what is happening. The mass point is freely sliding along the two rope that create a multi-segment rope. But we can do more now that we have this connection, 1D connection between them. We can do fun, interesting things with it. In example 5, we say, okay, let's grab this and hold on to it. So don't let it slide. We will control when it can slide and when it cannot, and that is done by using the 1D translational break. So MapleSim does have 1D domains that work with the 1D connection in the ropes and pulleys. So here, the 1D translational under the frictions and stops, there is a brake component. So by exerting a brake, I will stop the flow of material from one segment to another, causing this to stop. So the way I will run the simulation while I describe it. So the way it is done is that you will see that the initial offset is 1, but at 5 seconds into the simulation, the value of this step goes from 1 to 0, 1 minus 1, which means we will hold on and we'll stay where we are for the first 5 seconds, but after the 5th second, the mass starts to slide like the previous one. So we're going to run the simulation. We'll see nothing happening for 5 seconds because the brake is on. And there we go. Now we are back to what we were before. We can obviously reactivate the brake and capture the mass that is sliding on the 2 ropes. Again, just to describe the possibilities that this type of a causal modeling would bring into creating models representing systems that you might be looking at. Moving on to more, we can also use this connection to provide or like add or remove material from the setup that we have. I will jump over these 2 examples and hopefully you guys get to run them and look at the results and compare what is the difference between them and what is the results of those changes. So these 2 are a pair that should be run at one after the other and compare results. Moving on, so we can use that 1D connection to add and subtract rope, and we'll see other examples of that. We can also, just like you would expect, grab one end of a rope and pull it or move it, and causing the cascade of rope through the connected pieces. So let's do just that. I am going to go to example, what number was it? Number 9. So let's grab example number 9 and run that. So here we have again 2 segments for a rope. The point in the middle is fixed. I have a hanging mass on the far right, and I am grabbing the other end and moving it with this prescribed motion component. So here's the setup that I have. This point is fixed. This point is being pulled by the motion driver, and this is the free end that, as a result of pulling and pushing this length will change as well. So this will swing back and forth. Now I will move this, and the total length will remain the same as a result of this. So this is an abstraction for potentially a simple pulley system without any pulley. If the emphasis on the kinematics or how the forces work, you might even consider this simplification. As we will see next, that obviously you don't have to with the point ropes and pulleys, and you can increase your fidelity by actually incorporating a pulley in your system. So I will, we are at, so the other way of doing similar thing is not to move the ends, but providing additional material to the rope. So let's open number 6. I understand the ordering is a bit different here, but let's now open number 6, and both ends are fixed. The middle point is free, and we are adding material to the first one that causes this length to increase, and the dynamics between the 2 ropes and the sliding will decide how much rope goes to the other side. So this is all decided dynamically. We'll just increasing basically the total length and let the dynamics of the system decide on how the system will find a new balance. This is important to note, as these are the kind of dynamics that has been incorporated. Before running it, let's look at the signal that we have. So at 2 seconds, we are increasing over a time of 3 seconds, 2 meters. So we're adding 2 meters to this multi-rope segment as a model. And then at 12 seconds, we are removing that 2 meters that we added. So we go back to where we were. So let's run this. 1 second, we'll just constant everything. So the lengths increase, and this will just sit there and just slide without any more changes. And then at 12, we'll just come back to our original length and follow the same path as we were originally following. So an example of these last two examples show if you want to change the length of a multi-segment rope, you can grab one end or both ends, depending on your case, and move them, or you can use the 1D connection to add or remove rope from your system. The same would apply again for chains and cables, except that ropes would be the simplest and leanest model that you can create. Your fidelity requirement will dictate which one of these would be needed. We'll talk about chains and cables a little later. Okay, so let's go back to our guide and continue forward. So here's an interesting example of two objects that are, or one object's hanging with 4 identical ropes. Let's go quickly run this. So this was number 11. So let's open model number 11 and run that very quickly. So as you will see, if you have 4 parallel ropes between 2 objects, and the objects are rotating, the ropes will not see the same tension. And from a design standpoint, that might not be the expected outcome. As you can see, the 2 outer ones are taking most of the rope, but under certain angles that it's taking, we have almost a pulse-like tension going to the other 2. So how to fix that? One way would be to, as this slide shows, to kind of sew them together and make it one segment. So for that, we have to say side B has to be free on this one. I get my 1D port. A and B should be free on this one. A and B should be free on this one. And A should be free. Was it A? No, B. B should be free on this one. So let's just connect them together. So now these are connected to each other, and the rope can move. And sorry, not this one. I made a mistake. This one. Okay. Now here we go. So I'm going to zoom in to emphasize another important point. When we have segments like this, where the material is going to exchange between ropes, you have to make sure that the rope, the arrows that come with the icon kind of point to the same direction, and you don't break this continuity so that it has the same meaning as where the rope is going. So I'm going to save this result, the bad result, save this as original. And now that I've saved that, I'm going to run this model again with this modification that was applied to it. This way, the rope's length will change according to the kinematics of the system, because we're allowing that degree of freedom between them. And that will cause for a much smoother, as you see here, or better distribution of forces amongst all the rope pieces. This is obviously a simplified example that shows potential for doing this type of work, and in reality could be different in terms of implementation. Okay, so moving on, I have another example that hopefully you get to run. I will not run it here in this session, but this is how to expand what we just talked about even further, adding more elements from the multi-body or 1D rotational domains and create this robotics finger-like system that by pulling and pushing or pulling and releasing the sides left and right, we can create an action. We'll come back to this example once we talked about pulleys. So let's talk about pulleys now. This component, similar to the others in MapleSim, comes with the help documentation. And I want to let me just clean up a little bit here before I go to the first example that I have. I want to show you. Let me close these so I have more space. Here we are in pulleys. So you can look at the help page for the pulley, and it includes contains a lot of good information about how to connect them, most important features in terms of setting up your configuration, whether the rope goes under or over between the two. So we will see examples of these options are used, and whether we use the offset frame for the connection point versus the rotation point of the pulley with respect to its frame. So that option is available to you and simplifies some of the model creation. So I'll suggest to review the help pages for valuable information. Also, the tool comes with examples. It's embedded in it. So here, actually, I'm going to start introducing the pulley with examples from the example palette. This is the, as we just started with rope, this is the simplest. We have a fixed pulley with two ropes. One end is being controlled by us. The other one is free hanging mass. And we can change the length as we saw and see the effect of that. So low frequency vibration, as we decrease the length, the frequency goes higher as expected. So this is a first example of interacting with the pulley. We can obviously make that a bit more complex by adding a second pulley. So here's an example of a two pulley system, one fixed and one floating. So a floating pulley is also modeled with the same component. It has all the equations for multi-body equations for capturing its free motion in space. So we can connect almost similar to the previous one by adhering to the rule of order of arrows. As you can see here, we go all the way in the same direction in all connections. And create a model like that. I will let's look at the results. So here's our free pulley, and these are our fixed pulley, and we are removing material from this end, which causes the free pulley to pull up. You will have noticed that there is a new icon variation for the ropes. So let's just quickly look at that. So when we have a rope, a chain, or a cable, and we want to connect that to a pulley or a winch or the winch 3D, one thing you need to do first is you need to tell the components that there is a pulley to be connected to. So by saying pulley on end B, this icon appears. Now we make the connection to the pulley. So that's really important because the equations need to change. And those changes mostly are because we need to find out what is the tangent direction between the starting point and the unknown point at the start of simulation to the surface of the pulley, which is our tangent. So you will see in the examples that I'm showing from this point on that you need to use the options for connection to a pulley before connecting to a pulley, not after. So you select the option, then connect. Just as we saw with a group of connected multi-segment rope, for the rope chain and cable connected to pulley and winch, all of them together, you have to always make sure that you have unbroken direction of arrows for the components to make sure that you get the right simulations. So we have already started looking at the examples. We will come back to these examples as we go forward with the crane and the Flutter models and a slippage. But for now, we can look at another example. So this one is in your package of examples, number 13. So this is again another double pulley system, but literally with a twist. And just to emphasize that the library is 3D. A lot of examples that we saw so far are moving in plane, but the library can handle forces in all directions. The rope components or chain or cable do not have twist resistance, but they have, for the case of cables, they have bending resistance. So we'll move from that to this example. So this is example number 14. Let me open that up. Example number 14. So this is a gondola lift. I'm going to run that while I explain the model. So we have a speed control through torque exerted to one of the pulleys. So this is actuated, and is a very simple representation of the motor that moves, a closed system that we have a point in between two sections of the rope, just like those sliding masses that we have seen. We can use that to move something in between two pulleys. We won't be able to move something over the pulleys. That changes the structure of the equations, and that's something that is not allowed in this system that we are using, simulation software that we're using. So we can move things back and forth in between connection points, but not over a connection point. One other thing to note, we can look at the animation, then come back. So here it is hanging, and then the actuation is applied, and the torque, the forces are transmitted throughout the segments, causing the other pulleys to rotate as well. And we can for example, if this was representing a real system, analyze vibration, control signals, how good we are following the commanded signal for the position of the gondola. One thing to notice from this, as we have looked at the ropes, the initial length of the rope is selected as the two endpoints at the start of the simulation. So sometimes that does not create enough tension and causes a lot of sag. So we do have the option to apply pretension, which is selected for this system. We want everything to be have higher tension so that the hanging body does not sag too much. So here we can use pretension. So this is done in the unit of meters. So whatever length, for example, this segment end up being, the simulation starts with assuming the actual length of undeformed rope in between these 2 points is 10 meters less, causing a creation of a tension in this piece. We do the same for this other two, and at the start of simulation, tensions balance. So that's I think it would be my last example of introducing the pulleys. Let's get back to the slides. Yeah, so we have one more here. So I said that we come back to the robotic finger. So in the previous version of this that we saw, we grab the endpoint of the ropes and move them directly by applying 1D motion. Here, we made it maybe a slightly more realistic by connecting the rope pieces together, causing it to be a continuous piece, and the required the required force to move the finger was applied by a torque applied to the pulley. So another example of adding pulleys to more and more complex models. All right, so let's move on to chains and cables. So a chain and cable, again, I encourage you to take a look at the help pages for these components to see what's inside. Actually, we'll have a quick look at them when we get to some of the examples. So, so two examples I want to run here from the MapleSim. So let me jump back to MapleSim, go to help, examples, and ropes and pulleys, slippage. So I'm introducing two concepts together. So this is an example in MapleSim, again, a closed system of 3 pulleys. This is a representing a belt going around, 2 pulleys that can slip, and we have a tensioner or idler with a arm and a tensioning torque to be applied to it. Instead of, as we saw so far, using rope between these pulleys, we're using the chain component. So while this is running, let's have a quick look at the help page for chain. So chain is basically a series of ropes that are connected together, and in between there is a mass proportional to that segment of the rope. You can select how many mass points you want distributed in between the 2 frames representing the chain. The more you have, the higher frequencies you can capture, but it will be a heavier model to simulate. So you need to strike a balance between how much detail you want and how fast you want to formulate and run your simulation. So we are creating a ropes and pulleys example here, but using chain. So as you will see in the results of the animation, there is lateral motion in the chain pieces. As I talked about the fidelity, so this one is the larger one. I use 3 middle nodes for it, and these 2 smaller segments with less dynamics, I use 1 in between the 2 frames. So take a look at the animations. So one other piece here is that instead of arrows for the forces, I'm using the option for color coding. So the tension is represented as a variation of the colors. So let's run this again, maybe a bit slower, and see what is happening. So first, this idler is not exerting much force onto the rope. So the tension is low, and this is a driver, this is a driven. And we will see that the driven is not actually really moving because the slippage is happening. So driven is not gaining the velocity that it's supposed to have. Now we are tightening things up and run another cycle, and the driven reaches the intended velocity because the slippage was almost eliminated by increasing the tension. So that's one example to introduce the option for tension. Option for slippage, which is done under the slippage segment of the parameters, and by activating include slippage option, which gives you the option for the parameter visibility for the coefficient of friction. The other example that I want to show, this one to showcase 2 other features. One is the cable component, which is very similar to the chain component. I'm going to run this while I talk about the features of this very simple model, very reminiscent of what we had when we started this session, of a fixed point, a mass, and a rope segment in the middle. This time is a cable, and it has a few other things happening. So if I look at the help for a cable component, in terms of mass distribution is identical to chain, but this one will exert bending moment. So it has bending rigidity. On top of that, it can include, just like chain, it can include the wind speed, the effect of wind force on it with this well-known equations. You do have option to not use this equation as a lookup table. if you have a specific formulation available to you. And so this is angle of attack for each segment. So what we are doing here is, once the simulation is finished, I will rerun the simulation. We are increasing the wind speed slowly, causing the cable section to lift up. And as we reach a certain velocity, system goes unstable and exhibits the flutter behavior. So this example in the example palette, I encourage you to open it up and run it and examine its various parameters. So we are short on time, so let's go back to our presentation and see what would be the next step. Here we go. Okay, so there are 2 examples that I have included here for validation. One is a chain, a free chain should take the catenary form, so which is given by this hyperbolic cosine function. You should definitely run this and compare the results you get from here. A full segment and a half segment, identical results, but identical to the theory. The other one I will quickly run here is the natural frequency of the lateral vibration, which you can find in textbooks to be given by this equation. And we can do the same thing in MapleSim. So that was model number 17. So let me open model number 17. We're almost there. So number 17 is really a boring model because it really doesn't do anything. We have a constant with that equation that I showed, and we're just running this to have MapleSim evaluate this little expression, which we could have done in Maple or in a calculator. But to see that the model itself is actually not doing anything, it's a piece of chain that is connected between 2 fixed points. So when the results come up, we'll see that the value for that constant, which we have probed, this theory value, let's look at it. It is 3.535 Hertz for the predicted value. And as for the playback animation, nothing happens. It's under tension, it is not moving. But so how do we get validate the theory versus this model? We actually have to use one of the apps in MapleSim to extract the frequency content. So we go to the model analysis app, and the model analysis app will extract the equations and extract the underlying differential equation for getting the modes from the linearized version of the model. This will be done all behind the scenes. Quick look at how many points we had. So we only have 5 middle nodes selected. So the more we have, the closer we expect to be to theory, but this process will also take longer because we're dealing with more and more equations. So there are 5 steps to go through. Linearization would be the most important and the first one, and then analysis. And here we can see that the first mode of the vibration is actually 3.5 Hertz. And if I give you the Y view, we can actually see what the first mode is. So this kind of shows that the system with the linear spring between the segments and the mass distribution captures the expected theory of vibration. So let me move on. Here I have winches. This probably a lot of you have seen this. Is known as spool video. There's tons of videos about it online. So I thought maybe I should create a model and validate that with simulation as well. So if we go to MapleSim and run model number 18, so this is if it depends on what angle we are pulling, we will have different behavior happening. So let me just talk quickly about the model itself. So we have a 3D winch. And that 3D winch is enabled to contact the ground by the help of the contact library in MapleSim. So winch itself is just for the ropes and pulleys simulation, but there is nothing preventing you from expanding the model by adding machine elements for extra inertia or a contact torus for the other outer edges of the winch, and then the ground. So this is sitting on the ground, but also it's a winch that is free to move. So the winch can also be floating, just like the pulley that can be floating. So let's after the simulation, I will run the simulation again. So as many of you already knew, the first one, the left one, will come towards you as you pull on the string, and the right one goes away from you. And you can even play with this to find exactly what's the point that causes this to slide without rotation. So that's I thought it's a good example to introduce the 3D winch and all the complicated dynamic that goes with it. We do have additional models to go through. So this is one of the examples in MapleSim, which I will not open here in this session, but as you can see, it combines ropes for the less important pieces that we want. This is the part that holds the crane together. And we use the chain to use the cable system that lifts the load from the model. So do open this from the ropes and pulley example palette and run this. This example, let's go through this in MapleSim. Let me go here, file open, which number was that? Number 20. So let's open number 19 actually. Let's open number 19. So this is I've seen this done by students as a wall drawing robot. It's a gravity assisted cable robot that we are replicating here with, again, with chains to capture the dynamics, because this will not be perfect because gravity is the one that hold it together. A real cable robot for industrial application will have cables in all directions to make sure that the object is completely secure. This is not that. But we still want to somehow control the end effector or this mass hanging here to follow a certain path. So we do need to have an inverse kinematic. The point here that I wanted to make in this example is that the inverse kinematics is done by a copy of the model itself. We don't include the extra dynamics. So these ropes are replacing the chains in the actual model. And the ropes are made to exert compression force. The reason for it is the inverse kinematic is done with the reverse model. So we grab the end effector and move it around and have that motion transferred through the pulleys to the winches. And then winches are basically back driven. And we measure the angle for those winches and then send them out to the real system as the output of our inverse kinematic. So we're using a reverse model to perform in a really simple way the inverse kinematic for this system. We'll see that you can do the same approach for more and more complicated examples. I have two more examples to show. One is very simple and one is very fast because I'll leave the simulation to you guys. So this is the last model I will be running in this session in MapleSim. So let's we're watching the results updated as the integration is being performed, but we can then rerun the simulation after the fact. So let's look at this. For this less important pieces, I have one segment included, and for these ones I have 4. So I have in total 10 middle nodes that I have included, and we can actually take a look at those where they are by activating the primitives and turning off the CAD or the visualization for various pieces. So you can see where the middle nodes are. So let's turn it back to what it is and run the simulation so you can clearly see the lateral vibration of the rope pieces as they are commanded by the 2 winches, which themselves get their signal from the inverse model. So expanding this to more complex system would be something like this, with more pieces, and the same approach would apply, just to give you an idea of how this thing, something like this would be done. Exactly the same approach. The inverse kinematic block includes the reverse of the model that is being simulated or the target of our simulation. The last example that I have is taking this to the more detailed. And for that, I have included the FMU. So all models we create in MapleSim, you can export them as FMU, and that FMU is the gateway to incorporate that in other parts of your tool chain, whether it's an automation case or other projects that can understand FMU. We can also package our models in just pure C code or other formats, but FMU being popular and becoming more and more popular each day. So I've included this cable robot. The source of it is a paper I found. So I used, inspired by what they have done. So this has a lot more ropes and pulleys in there. So I've already created the FMU for this, and that FMU has put in the package that you have. So I will just double click to run the FMU here, but on your side, you need to open the Insight software first, and then use the file open option in the Insight to open this FMU. Once the FMU is open, we both reach this point. We see the model, which is not in MapleSim anymore. We don't need to generate the equations. Everything is done for us. So I will go to this for running the simulation, and I can just run this. So we'll run the simulation, and if you open the tunable parameters, which I included in the export, I can change these values and have the robot interact with the commands that I'm giving it. So the inverse kinematic, as we saw in a simple example, is implemented here as well. So I can move this to any point that I want by changing the parameters. In a real examples, obviously, this will be done from the command you get from your PLC, which you can pass along to the FMU or to Insight to perform a task like virtual commissioning. So this was a overview of the ropes and pulleys library in MapleSim, and the last part being what you can do to export that for further down your tool chain. So the Insight, MapleSim Insight is a separate program than MapleSim, and you can use that for visualization when you're running your FMU by streaming values to it. You can have it run the FMU directly, just this example that we saw, or you can use Maple Insight package to access it programmatically. So those are the three options that are available to you. So with that, I finished my presentation, and hope that it was of interest and provided some good information to you.